Today's notes are on Charles's and Gay-Lussac's laws. First of all, Charles' law was founded by Jacques Charles, 1787. He got extremely lucky. He didn't publish his work. He was a French physicist, lived in the 1700s. He found that oxygen, nitrogen, hydrogen, carbon dioxide, and air expand to the same extent with increases in temperature. So Boyle, remember from yesterday, studied pressure and volume. Charles studied temperature and volume. He also was the inventor of the hydrogen-filled balloon, and on December 1st, 1783, he ascended into the air in his hot air balloon. Again, he hadn't published his work in 1787, and he got very lucky that the man who discovered his work, Joseph Louis Gay-Lussac, in 1802, gave him credit for the work that he did. So just like Boyle's law that we learned yesterday, Charles' law is going to have some constants. In Charles' law, we have constant pressure and constant moles. Again, when we talk about moles, we're talking about the amount of gas. So how much stuff there is, how many particles. So Charles discovered and practiced with volume and temperature. So at constant pressure in moles, volume divided by temperature is always constant. So for any given sample of gas, an individual unique sample of gas, volume divided by temperature will always be the same. So just like Boyle's law, we are going to now compare and use and find a constant here for Charles' law. So volume divided by temperature is always equal to the constant K with a little c, subscript c for Charles. Unlike Boyle's law, this is a direct relationship. When one goes down, the other one goes down. If one goes up, the other one goes up. Because we're dividing this time instead of multiplying, they are going the same direction. One goes up, the other one goes up, one goes down, the other one goes down. So again, if we put two of those relationships together, we get what we actually use and express Charles' law as. So V1 over T1 is equal to V2 over T2. So we have, again, an initial set of circumstances and a new set of circumstances. One warning as you are doing all the problems in your homework today, most of the time the temperature will be given in Celsius. You must make that conversion to Kelvin. All temperatures must be in Kelvin. You will not get the correct answer if you use Celsius. So let's take a look at a little example again, just like we did for Boyle's law yesterday. We have a sample of gas at 15 degrees Celsius and 1 atmosphere. It has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? So again, we got to take a look at our data and information in the problem. We have two pressures, but they're the same. So again, pressure is being held constant here. So we need to convert our temperatures to Kelvin. So to get to Kelvin, remember you are going to take degrees Celsius plus 273.15. Watch your sig figs since there's nothing after the decimal, after the 15 and the 38. We aren't going to have any digits after the decimal in our numbers. So 15 degrees Celsius would be 288 Kelvin. 38 degrees Celsius is 311 Kelvin. Now, as we look at the wording in here, our gas sample is at 15 degrees Celsius and has a volume of 2.58 liters. Okay, so I know that these two things go together. So the 2.58 liters goes with the 288 Kelvin. Volume over temperature is equal to, we're looking for the new volume at the new temperature. To solve for x in this case, no matter whether your x is on the top or the bottom, mathematically, we are going to cross multiply and divide by the one that is multiplied with the x. So I will multiply together 2.58 liters and 311 Kelvin, and I would multiply the x and the 288 together, which means when I get this product here from the 2.58 and the 311, I will divide by 288, which was with the x, to get rid of that and get the x isolated by itself. So your answer will be 2.79 liters. Now, I would highly recommend that you take a few moments and sketch the graph that you see over on the side. A few people asked in class a little bit about how do we know that absolute zero is the lowest temperature possible? Well, we haven't actually gotten all the way to absolute zero, but scientists are pretty sure that this is correct. Again, of course, this is science. Things do change quite frequently. But in this case, we think that it is pretty well set that the absolute zero is minus 273.15 degrees Celsius. Here's how they figured that out. They've taken samples of all kinds of different gases, and you can see some of the data here in this graph. So here this line, this one is helium. We see that as temperature decreases, volume decreases, just what we were looking at with Charles' law. So a lot of the data that was collected by some of these early scientists has been rechecked by scientists nowadays, and they're still finding out the same thing. All of these gases, when we measure their volume at decreasing temperature, even though they're starting at different points, all right, different volumes because of the sizes of the molecules, okay, all of those things, so they're all converging at that same point. If we graph this data and extrapolate, that's what's happening here with these dashed lines. They don't have to have perfect data all the way to the end. Those dashed lines are an extrapolation of that line, continuing that straight trend all the way out. They all converge at the same point, and that point is absolute zero, which is minus 273.15 degrees Celsius. So pretty neat. So if you need to pause, make sure that you pause at any time during this recording, catch yourself up on the notes, and then go back and listen again as needed. Our second gas law today is Gay-Lussac's law. Again, he was the one who discovered Charles's work, was kind enough to give him credit. He was a French chemist and physicist, lived in the 17 and 1800s. Also a hot air balloonist, just like Charles was. So in 1804, he ascended 5 kilometers in a hot air balloon with Jean-Baptiste Biot. All right, pretty good for that time in a very early hot air balloon. He also, in 1805, discovered that the basic composition of the atmosphere does not change with decreasing pressure. All right, so basically there's the same type and percentage of molecules in every part of the atmosphere, regardless of where you are at in the atmosphere. So all of his work and time that he spent in his hot air balloon, he was collecting samples and running scientific experiments. One other discovery in 1808 that is credited to Gay-Lussac is that he was the co-discoverer of boron, the element boron. All right, so putting together his work, very similar to what we just looked at with Charles' law, Gay-Lussac's law focuses in on pressure and temperature. All right, and he found that at constant volume and moles, again, the amount of gas trapped in the container he's working with is going to be the same. That pressure divided by temperature is always constant. Again, therefore, we can express that as P divided by T is equal to the constant Kg, G for Gay-Lussac's. Again, a direct relationship because we're dividing. When one goes down, the other one goes down. When one goes up, the other one goes up. In order for that to be remain constant, they both have to go down or they both have to go up. So when we combine two expressions together, we get P1 over T1 is equal to P2 over T2. Again, an initial set, the P1 and the T1, versus the new set, the P2 and the T2. Just like in Charles' law, in this problem, anytime you are using temperature, that temperature has to be in Kelvin or you will not get the correct answer. I didn't put a separate sample on this one as a practice calculation. You've got several in the homework that you can work on. It's the same process as Charles' law. Key things that you want to keep in mind as you're working on the problems in the homework is that you have consistent units for your pressures. You have to make sure that they're both in atmospheres or both in millimeters of mercury. So sometimes they're going to make you convert, so pay attention to what they give you. And no matter what, your temperature has to be in Kelvin. All right, have a great day and have a great weekend, and I will see you on Monday.